And we're good to go. Okay, so starting off right away, chapter 2, mechanics. So first part, motion. So position is simply the coordinates of a particle on a line or on a plane. It's basically what you do in math with the coordinate system, though you don't have to dwell much on it for physics. Now moving on to our vector quantities and scalar quantities. So vector quantity is anything that has a magnitude and direction, and scalar quantities are those, well, they're basically just numbers or constants. So let's make a comparison between displacement and distance. Displacement is just the vector version of distance. So for displacement, you just take the shortest distance between 2 points, and that is your displacement. Oops. So that's going to be a displacement, which is usually given by the symbol s. Meanwhile, it doesn't matter whether you go from this point to this point like this, or whether you go like this. Your displacement is just going to be the shortest line connecting these two. Meanwhile, your distance will actually be the length of these lines that you've taken in order to come to this point. Next, we have velocity. Velocity is just the rate of change of displacement, or basically how fast an object is going. So velocity is just a change in displacement over change in time. Meanwhile, speed is a change in distance over change in time. Next, acceleration. Acceleration is simply just the rate of change of speed over time. So change in velocity over change in time. So using all of these, we can come up with our Suvat equations. All of these are in the data booklet. I can quickly go over as to how we arrive at each of these. So let's take a look at the first one. So from our definition of acceleration, we know acceleration is the change in velocity over change in time. And change in velocity is just simply the final velocity, which I'll be calling v. That's what we normally use in order to show final velocity, v or vf, and minus our initial velocity, which is u, over the change in time. So if we rearrange this equation, we end up with our final velocity minus our initial velocity is equal to acceleration times the change in time. So you end up with our final velocity is equal to our initial velocity plus acceleration times the change in time, which is our first Suvat equation. For our next one, we're going to make use of this again. So our definition of velocity is that it is the change in displacement over the change in time. So another way, so we know that from earlier that our final velocity, or our velocity, is equal to the initial velocity plus the acceleration times the change in time. So if we bring that in over here, we have initial velocity plus acceleration times the change in time, or I can just call it time for now, because we're just assuming that the initial time, we start at time equals 0, is equal to the change in displacement over time. So if we rearrange it once again, we end up with displacement equals to initial velocity times time plus, oh wait, sorry, oops, I seem to have missed out something. Okay, so sorry, just give me a second. Basically, our average velocity, this expression is for average velocity, not final velocity. Sorry, I kind of mumbled that up. So our average velocity is equal to the change in displacement over change in time, which means you can also put it out as our average velocity equals to our final velocity plus initial velocity divided by 2, and that is equal to our displacement, change in displacement over time. So if you bring our term back over here, we end up with final velocity times time plus initial velocity times time divided by 2 is equal to the change in displacement. So note we have our final velocity term over here in terms of initial velocity and acceleration. So we can sub that in for our final velocity over here, and we end up with u plus at times t plus initial velocity times time divided by 2 equals to the change in displacement. So we end up with, if we rearrange this a bit, we end up with our displacement is equal to 2 times initial velocity times time plus acceleration times time squared divided by 2, which simplifies into final velocity plus acceleration times time squared divided by 2, which is our second kinematics equation. And yeah. Actually, these ones just take it. I actually won't go over the next two ones because it'll take quite a while. So, but we have these other equations. That is final velocity squared equals to initial velocity squared plus 2 times acceleration times displacement, and displacement equals to initial velocity plus final velocity times time divided by 2. And these are all in your data booklet, so you don't really have to memorize them. Next, for any falling object, the acceleration, it will always experience a constant acceleration, and that acceleration, assuming it's falling on Earth, will be equal to g, or 9.81 meters per second squared. Okay, next up we have projectile motion. Projectile motion is something that people tend to find difficult in this chapter, so I'll go over this in detail. Okay, so let's say let's take an example case over here to explain this. Let's say that's a guy over here. Let's say let's say that's Lewandowski over there, and he's trying to take a shot into the goal. So he kicks the ball goes up in an arc-like shape and lands into the goal. So now we can make a few simple calculations from here. So when he kicks the ball with an initial velocity of u, let's say. So now how do we calculate things such as how far has the ball gone, or how long will it take for the ball to land? Well, for that, first thing that we should do is we should split this into two components, into the velocity in the x direction, or the velocity that's going towards the goal, and the velocity in the y direction, the one that points upwards. So if you notice over here, we actually have a right angle triangle. Let me just draw it up over here so it's a little nicer to look at. So we have our initial velocity over here, and that's our y component of velocity and our x component of velocity. So now let's come up with some values for these. So our Vx is going to be equal to, let's say he shoots it up at an angle of theta. And so the velocity in the x direction will be simply u, which is our initial velocity, times the cosine of theta. So that's going to be our velocity in the x component. Now our velocity in the y component will be theta is over here. So it's just u sine of theta. But if you realize over here, the ball is going up, and we know that gravity is constantly pulling us down. We have a constant downwards acceleration of g equals to 9.81 meters per second. This is constantly acting downwards. So at any given point of time, our y component of velocity will be equal to the initial velocity times sine of theta minus g times time, whatever the time has passed. And that's going to be our Vy. And now if you notice over here, as the ball goes from, as the ball gets shot and enters the goalpost, its y displacement in the y-axis, or its displacement in the up-down plane, is 0. It doesn't move anywhere. But meanwhile, its displacement in the x-axis, there's some displacement happening in the x-axis, which I'm going to call as s. So how do we find out this s? Well, we know that we have a x component of velocity that's constantly going over here, and there are no other forces, at least that we're aware of, that's acting in the x direction. So it's always going to have this velocity x, which means our displacement s will be equal to velocity in the x component times time, which is also equal to u cos of theta times time. Yeah. And that's basically the equations that will help you to calculate something for projectile motion. And also note, when the ball has exactly had a displacement of s by 2, or when it displaces half, at one stage our Vy will be equal to 0. We won't have any y component velocity. So that is actually when our object has covered half of its motion. So whenever you're given a question like this, your general aim is to try and find out at what time it reaches this maximum height over here, this maximum height of h. So at that point, you just make your Vy equal to 0 and then solve for t. And then you can find out your displacement by multiplying the t value by 2, because remember, it's just gone half the way, and you can end up with your displacement. Yep. Yeah. And yeah, air resistance is always ignored unless stated otherwise. Well, I haven't really seen a case where they make you do any calculations related to air resistance. But one thing you should know is that the path of a ball or any object that's going through projectile motion, its path will look slightly different, something about like this, when there's air resistance. So it's a commonly asked MCQ, so it's good to keep that in mind. All right, now terminal velocity. Well, terminal velocity is the maximum velocity of any freely falling object when there is air resistance present. So basically, our air resistance causes an acceleration upwards when something is falling downwards. So due to air resistance, at one stage your velocity will stop changing. You reach a maximum velocity, which is called terminal velocity. Now, you just need to know the definition of it for IB, but in case they ever ask you, there's somewhat of a formula. It's not really a proper formula, but it's the mass of the object times gravity divided by some constant k that they give to you. But I really doubt they ever ask you about it, and this isn't really a proper formula, so better not to refer to it. And that's it for the first part 2.1. Are there any questions before I proceed? Or are we all good? Will it be strictly parabolic for air resistance? No, it actually won't exactly be parabolic. So it goes like this, and then it has a little sharp dip towards the end. Well, my drawing's a bit rough, but let me try and do it as close as I can. So something like that, and then there's a bit of a rough dip. So like this arc is smaller than this arc, something like that. But well, you really won't have to do any calculations with it. So just know like the general shape. All right. I think I'll move on. I'm going to assume that there are no other questions, unless you guys want to pop up something quickly. I'll be sure to get back to it later. Let's move on to the second part, forces. So what is a force? Force is simply a push, pull, or a twist exerted on an object. It's a vector quantity, and forces always cause some form of acceleration. And weight is simply a force that results of the gravitational attraction between a planet and an object. Well, basically, if you remember earlier, we talked about there being a constant acceleration downwards called g. Well, since it's something that's causing acceleration, it's pretty much a force since it's pulling things downwards. So that specific force, the force due to gravity, is called weight. And we have some simple formulas. We have F equals to ma, mass times acceleration, for calculating the force exerted by any object. And weight is equal to mass times gravity, or the gravitational acceleration, which is 9.81 in case of Earth. And that's just the value for weight. And force is always measured in newtons. Yeah, and here's one more thing though. For chapter 2, you really won't have to look much into it. This is more important when you look at chapter 10. That's the HL part. But the constant g is actually dependent on the position of the object in a gravitational field. So basically, it's not exactly constant, but because Earth is, our planet is so large that for the calculations that we take, it's approximately the same throughout. So you can just assume it to be constant at 9.81. Okay, so tension. So tension is a force that arises when compressing an object or stretching an object. The source of this tension force is due to the electromagnetic interactions between the molecules and the objects, but you don't really need to know much about that. One commonly, the common places where you see tension is, let's say you have someone over here, he's got a rope, and then there's a box over here, and he's pulling the box. He's trying to move in front and pull the box. And now this rope stretches up a bit, and so we say the rope has some kind of tension in it. So it has some tension force in it, Ft. That's allowing this block over here to move in front. And yeah, the formula for tension is, well, actually the tension can also be used. Tension and spring force pretty much have the same formula, so they can be used interchangeably. So tension equals to actually minus kx, where k is a given spring constant or a constant that's given to you, and x is how much it's been compressed by. Why is it negative? Because, well, if you remember, I told you that it's a vector quantity. And if you think about it, let's say we've got a spring over here, and it's attached to some kind of block over here, let's say a very sturdy block, and you push onto the spring, you actually feel a force acting backwards, and that is the force that's the spring force or the tension force, as it always has a tendency to go towards its equilibrium point or its normal state. Okay, so next, normal force or reaction force. This is a force that is generated when two objects are in contact. This force will always act perpendicular to the surface of the object and also originates from electromagnetic forces. Well, a common example of the normal force is if you, let's say, have a table and you place an object on it. So now we know that our object will be experiencing some kind of gravitational force that's constantly pulling it down. Yet our object remains still on the table. That's because we have a normal force that is acting back on it. And note the normal force will always be perpendicular to the surface. So like this table is completely horizontal, so our normal force acts vertical. However, if you have, let's say, another example, like let's say a ramp over here, and you have our block that's sitting over here, our normal force will act upwards in this way. That's where our normal force is, even though our weight acts directly downwards. But we'll look like more of that when we talk about free body diagrams. Next, we have drag forces. So drag forces is anything that opposes motion when an object is in motion in a fluid. So you can think about it like, let's say when you go for swimming, where when you try to swim in front, it feels like something is slowing you down. Well, that's basically the drag force. And air resistance is an example of drag force because air is technically a fluid. Upthrust. So upthrust is an upward force faced by objects in free fall in a fluid. So let's say when you're falling from the sky, or you're falling or you're sinking in water, you face some kind of upthrust. An example of where, okay, and also if the upthrust is stronger or exceeds the weight, meaning it has a larger magnitude than weight, then the object will float or fly. And vice versa, as in if the weight is larger than the upthrust, then the object will sink or fall. And an example of where you see the upthrust is in action, like helping people go up instead of your normal downward fall. If you ever see a skydiver that's falling, and then all of a sudden he opens his parachute, for a few seconds, it's like he or she will go upwards and then start going down again. Well, when initially the person pops open the parachute, there's an upward force, or the upthrust is significantly larger than his weight, so he ends up going up for a bit. Frictional forces. Okay, so frictional, this is something that I'm sure all of us are familiar with. These are forces that oppose the motion of solids on other solids. If you have, let's say, like me sliding the mouse on my table, there's some kind of friction that acts over here. Or maybe if you, let's say, roll a cart across a table or across the floor, there's some kind of friction that acts. So as long as there's some kind of contact between the two objects, there's going to be a frictional force that will constantly oppose the motion, as in act in the opposite direction in which the object is moving. So you've got two types of friction. You have dynamic friction. This is the force generated to oppose the tendency of motion. So you have a simple formula for this. So the dynamic friction force is equal to a constant mu sub k. That's a constant that will be either given to you or you need to find out, times the normal force that acts on an object. So it's entirely dependent on the normal force that is on the object. I've used R over here, but you can use N as well, but R is just the normal force. Now static friction is the force required in order to make an object move. So you can think about like static friction. If you have, let's say, a box that's already sitting on the floor on a carpet, and if you try to push it, you notice that unless you start pushing it with a certain amount of force or apply some amount of strength onto it, it doesn't really move. And this is because of static friction. And I noticed there's a small error in my static friction formula, but static friction is less than or equal to the static friction coefficient times the normal. Very similar to our friction, our dynamic friction. It's just that it's less than and equal to this time. That's because static friction can vary depending on the scenario. Okay, why does static, well, why are we really talking about this? Well, I think I should explain what net force is by now. I should have put one line about net force in this talk. I'll make sure to do that. Okay, so net force. Net force is basically the sum of all the forces that act on an object. So if you have an object and let's say there are two ropes attached to it. There's a guy over here who's pulling it with 10 newtons, and there's another guy over here who's pulling it with 12 newtons. Well, the net force that acts on the block will just be 12 minus 10. Well, that's because it's a vector quantity and we're taking this direction to be positive. So we end up with the net force being 2 newtons. Okay, free body diagrams. So free body diagrams, this is really important. I highly recommend everyone to draw a free body diagram whenever you've been given a question related to forces. It really helps you to visualize the problem and see what exactly you need to solve for. So it's just basically drawing those line diagrams that I've been doing until now, except I didn't really refer to them as free body diagrams, but that's what they basically are. You just draw the object and all the forces that are acting upon it to show, basically, in order to help aid you with your calculations. I'll do an example of free body diagrams along with frictional forces once I have gone over the laws of motion real quick. Okay, let me just check for a second. Okay, cool. We're looking good so far. Okay, so the laws of motion. Well, there are three laws of motion, Newton's three laws of motion. The first law of motion is when the net force of an object is zero. Well, when the sum of all the forces on an object is zero, the object will move with a constant velocity. Note, constant velocity also means zero velocity, so it can stay completely still as well. So that's your first law of motion. The second law of motion states that the net force of a body with constant mass is proportional to its acceleration. So this is just saying force is proportional to acceleration, and well, if we add in the constant mass, we just get our force formula again. That's essentially what our second law of motion is saying. And it also says, like, the larger the net force on a body, the larger its acceleration, assuming its mass remains the same. Last, we have Newton's third law of motion, which people like to reference to a lot in different ways that aren't actually what they are. So the third law of motion is simply that every force exerted will have an equal and opposite reaction. Well, the simple example of this is your normal force. Your normal force is an example of the third law of motion. There's the weight that acts down on the table, if we take the example of the block sitting on a table, and the normal force acts backwards on it. Cool. I think I'll just do a quick example of an example with friction and free body diagrams to, like, maybe make things a little clear. I'll look at our favorite ramp problems. Okay, let's say we have a block that's sitting on a ramp over here. There's a block that's sitting on this ramp and it has a mass of m, and this is a realistic ramp, so it has a friction, it's frictional, it's not frictionless, and it has a coefficient of friction of mu sub k, coefficient of, like, of kinetic friction as mu sub k and coefficient of static friction as mu sub s. So let's try and draw some free body diagrams on this to really help us visualize the case that we're looking at over here. So let's say we have, so we know that there's going to be a weight that acts downwards. That's our weight. And we have a normal force that's acting perpendicular to the plane, though the normal force isn't as big. All right, I completely forgot to mention, it's angled at an angle of theta. And we have some kind of frictional force that's acting in this way, keeping the block up, called F. I'm just going to call it FF. Okay, so now let's try and figure out what our exact values are over here. So our normal force will actually be smaller than our weight because it's the part of the weight that's acting into the ramp. So we can once again take our weight into two components, a component that acts into the ramp and a component that acts down the ramp. Our normal force will be equal to the component that acts into the ramp. And actually, this triangle that I've drawn over here is a similar triangle to our ramp over here. So this angle here is theta, which means our normal force is now going to be equal to mg cosine of theta. Note, the normal is not just mg, so you have to make sure to use mg cosine theta every single time. Okay. Now we have a component that's acting downwards down the ramp, which I'm just going to call as FA. So our FA will be equal to mg sine of theta. So now if this was a frictionless ramp, we just say, okay, there's a force of mg sine theta that's acting downwards. So if you're, let's say, to find the acceleration of this block that's going down, you just get rid of the mass, and g sine theta is your acceleration down the ramp. But we have friction acting over here. So let's try and calculate the net force over here. So I'm going to use a little weird axis over here. I'm going to say this direction is our y-axis, our positive y-axis, and this direction here is our x-axis. So let's try and see what forces act in which direction. So in our y-plane, or the forces that are acting up or down the ramp, the perpendicular of the ramp, we know there's a normal force that's acting up, and we know that there's a component of gravity that's acting inside, mg cos of theta. We know our normal and mg cos of theta is 0, so there's no motion in the y direction over here because our net force is 0. So now if we take in our x-plane, we see things a little different over here. So we know in our positive x-plane we have a force of Fa acting down the ramp, minus a force of F friction that's acting up the ramp. So our Fa is just going to be mg sine theta. And note, our friction won't exactly be like, if you know, will be our coefficient of kinetic or static friction depending on whether the object is moving or not, times the normal force that's given over here. You have to use this normal force, not just mg. You have to do mg cos theta and make sure that you do it. And like that, you should be able to carry out any calculation related to ramps. And I believe that's it for 2.2. Before I move on, are there any questions? Anything you'd like me to ask to me or go over? Yikes. I'll actually avoid using calculus, though I can do something interesting at the end if you'd like. Sorry, I didn't read that earlier. About the x friction, okay. So basically, I'm going to now get rid of some stuff so that we can look at it clearly. So let's get rid of a few things over here so I have a bit more space to talk about it. Okay, so normally for our frictional force, we say it is the coefficient of friction, let's say kinetic friction. Let's say this is going down and then we have a frictional force that's acting upwards. So we know that it's mu sub k times r, that's our normal force. Normally we just take our normal force to be mg, which is a common mistake that people tend to make. But in actuality, what you need to do over here is do mu sub k times mg cosine of theta. You have to make sure to include this cosine of theta part because your normal force isn't as large as it would be on, let's say, a flat surface. Does that make it a bit more clearer? Why is the friction force equal to the coefficient of normal times coefficient times the normal force? Okay, so after experimentation and observing things, we noticed that the frictional force is proportional to the normal force. Depending on our frictional force increases proportionally with our normal force. So what we just simply did is, in order to make this into an equation, we just created a constant mu sub k, and just multiply that with the normal force to give us an equation. But we we pretty much noticed, as we have a larger mass, or as we have something that's generating a larger normal force, we have a larger frictional force acting on it. That's pretty much it. Well, okay, if you want, I can go in depth into why, why they're proportional to each other, if you really want me to. Okay. All right, let's do this. Okay. So let's look at a simple example over here. Let's just say we have a block that's over here. So now we know that there's a weight that's acting downwards, right? And now we know that there's also a normal force that's acting upwards. But where exactly does our normal force come from? Well, to look at this, well, even more in depth, is if you look at the molecules that are there on the surface of the table. This is just an approximate drawing. Let's say they're normally like this. They're all very well leveled, and it's pretty much almost flat. They're just so close to each other and so well aligned. Now when you place your block onto this one, what actually ends up happening is your things get pushed down a little bit and creates some kind of tension between the molecules, because there's a force that normally keeps them together and now they're being pushed away, so there's a larger tension force in between these molecules, and this results in an upward force on the block. So as our block gets larger and larger, it pushes down even more, and as a result of which, if we think about it, it makes it even harder to push away or get them to move across this, because you end up creating a larger bump in your surface. And that's exactly why your frictional force increases proportionally with your normal force. If that helps. Does that make sense? Cool. Okay. Right, and there's one thing I forgot to mention. So earlier I talked about static friction being less than or equal to the coefficient of static friction times the normal force. Actually, I should use R because I used that in my notes just to avoid confusion. Yeah. The reason for this is our Newton's second law. Let's say we have a object over here, and this time I'm actually going to make use of numbers so that I can really show. So it's standing still. There's a coefficient of static friction of 0.5, and the normal force acting on this is 100 newtons. So now let's say you start pushing the block, and because you're trying to push it in this direction, there's a frictional force acting in the opposite direction on the block. But let's say now you're pushing it with a force of 50 newtons. Now, if we just said that our static friction is equal to the coefficient of static friction times the okay, actually, let's not use 50, that's a bad choice. Let's say 40 newtons. So we know that our static friction acting backwards or against the motion will be equal to 50 newtons from our formula. Now our 50 newtons that acts backwards is larger than our 40 newtons that acts forwards. Now this results in a net force of -10, meaning our block should actually move backwards, but it doesn't. So what this basically shows is that our static friction adjusts according to what kind of force is acting on it so that the object stays still. And our coefficient of static friction times the normal is simply the maximum static friction that can act on an object. Yeah, and that's that. Moving on to 2.3, which is work, energy, and power. So work done. What is work done? Work done is simply the force exerted in the direction of motion and the displacement that occurs. So the formula is Fs cosine of theta. Why is it cosine of theta? Well, okay, so I said it's just simply the product of the force in the direction of the motion and the displacement. But let's say you have, let's do another example with the block. Yes, we love using blocks in motion. So it's being pulled at an angle of theta over here. Someone's pulling it at an angle of theta. Well, basically, the y component of this force that he's applying over here does not really cause any kind of displacement on the block. It isn't really making it displace in any way. So we just completely ignore that and we just look at the x component, which is F cosine of theta. And we multiply that with our displacement. And that is our work done formula. Work done is measured in joules, which is the same unit as energy as well. Okay, next we have kinetic energy. Kinetic energy is basically the energy that's present in a body that's moving. Kinetic energy is given by the formula half mv squared. Yeah. And that's pretty much all that you need to know. They may ask you to calculate the kinetic energy at some point. It's really simple. You just plug in the mass, you plug in the velocity of the object over here, and you just get your kinetic energy. Now, next we have gravitational potential energy. Gravitational potential energy is the energy possessed by an object placed in a gravitational field. Well, to put it in a little bit of a layman term or a simple way, it's basically the potential work that gravity can act on an object. Let's say we're holding a ball up at a height of h, and we know that there's a weight force that's acting downwards. So let's say that's someone holding it with a very weird looking hand. We have a weight that's constantly acting downwards and a height. Now if a person lets go of it and this ball falls all the way down the height h, the work done due to gravity will be the weight times the height, or mgh. So basically it's just how much work gravity can potentially act on an object. And note it's always relative, so it doesn't have to be the absolute height from somewhere. You can take it relative to any point, the height relative to a certain point, and just use that in your potential energy formula. And that is your potential energy, GPE. Okay, I think I should say a quick thing about conservation of energy. So there's a theorem called conservation of energy, which says energy can neither be created or destroyed. So basically, the total energy of a system before and after will always be equal to each other. And note, we've pretty much just talked about two energies over here, kinetic energy and potential energy. So you can see our initial kinetic energy plus our initial potential energy will always be equal to our final kinetic energy plus our final potential energy. Okay? Yeah, cool. All right. And I guess I should also add this in. There's also the work energy theorem, though I'm not sure whether the IB requires you to know this, but one thing you should keep in mind is the work done is equal to the change in kinetic energy. So if you apply some kind of force on an object and it does a work of, let's say, W, that W is also going to be how much by which your kinetic energy has changed. And note the conservation of energy formula I said only applies when you only have kinetic and potential energy in a system. You have to be aware of losses of energy to things such as friction. Maybe I can add that in. The work done by friction or the energy lost to friction, I'm just call that WF, is just simply a frictional force times the distance over which it acts, or just mu sub k times the normal force times the distance over which it acts. And note this results in a loss of energy to the system. So you have to keep that in mind. All right, power. Well, power is just simply the rate at which work is done, the change in work done over the change in time. Another way to give power is force times velocity. How do we get that equation? Well, it's simple. So we have power equals to change in work over change in time. And our change in work, well, let's say we have a constant force that's acting. So it's work times the change in displacement over the change in time. Oh, look over here. What is this? Change in displacement over change in time. That's just our velocity. And boom. There you have it. And power is given with the units watts. Efficiency, well, efficiency is just the ratio of useful energy or power output to the input energy or power. Oh crap, I meant to write input over here. That's input. Okay, so basically, if you want to calculate the efficiency of a system, you just do initial energy over final energy. Sorry, no, final energy over initial energy, or final power over initial power. And I believe that should be all for 2.3. I can do an example if you guys would like. Any questions or if you want me to go over an example, I can do that. Okay, actually, I should have done this, but I kind of forgot to do it. Okay, so I don't exactly have a past paper question, but I can make up something that you might get to see in an IB exam. Cool. Okay, so let's say we've got a huge ramp over here. Okay, and we have, let's make this a little interesting. Let's say we've got a guy with a skateboard up here. All right, so he goes down a ramp, and then there's a flat surface, and then there's another ramp over here. Okay, so let's say we're going to try and calculate whether he will be able to make this jump over here or not. That should be a fun example to do. So let's get some numbers in. Let's say this has a height of 100 meters. The ramp is frictionless to make things a little easier for us. This dude over here has a mass of 50 kgs. He has a mass of 50 kgs, and this region over here is a bit rough. It's not really a smooth place, so we've got some friction that will be acting on us over here. So let's say it has a coefficient of friction of 0.2 to keep things a little simple. And our tiny ramp over here has a height of 50 meters. And this stretch over here has a length of this stretch. Let's see. I think I'll make this 25 meters. Cool. Let's try and figure out whether our boy over here will be able to make the jump, or will he just fail at it and just roll back down. Okay, so we know that he has some potential energy over here, gravitational potential energy over here, GPE. And as he goes down, this gets converted into kinetic energy. So let's try and figure out how much kinetic energy he will have once he's down here. He moves with the velocity of v, so let's try and figure out how much kinetic energy he's going to have at that point over there. So this is frictionless. There's only gravity happening over here, or the gravity that's bringing him down. He's not pushing out anything, which means our potential energy initial will be equal to our kinetic energy at the bottom of the ramp, our kinetic energy final. And now from our potential energy formula, we know it's just mgh. Our m is 50, our g is 9.81, and our height is 100 meters. Let me just plug these numbers in real quick. So 50 times 9.81 times 100, and that gives us 49050 joules. So this is his initial potential energy, and also the kinetic energy that he has once he enters this rough region over here. So now, as he goes over here, because of the friction, he's going to slow down a bit. And also, we're aware that friction is a force, so it applies some kind of work on, it does some work on the skater boy, I'll call him skater boy, I guess. And as a result of which, his kinetic energy will decrease. And from our work energy theorem, the one I mentioned to you earlier, the work done is the change in kinetic energy. So basically, his kinetic energy when he arrives over here at this point over here, right before our ramp once again, will be equal to 49050 minus the work done by friction, which I'll just call WF for now. So now what is our work done by friction over here going to be? 49050 minus, oops, my mouse is not really being cooperative today, but that's okay. 0.2 times the force by friction is the normal force. Since it's completely flat, the normal force is just going to be mg, 50 times 9.81, so 0.2 times 50 times 9.81 times the length over which it acts, which is 25 meters. And so we end up with 0.2 times 50 times 9.81 times 25, which is equal to 49050 minus 245.2.1, sorry, 5. So it's lucky that he doesn't really lose much energy or speed over here, or velocity over here. So he might actually be able to make the jump. 46597.5 joules. Okay, so this is the kinetic energy that he has right before he goes up the ramp. So will he be able to make it? Yes. Well, actually, I should prove it with the calculation instead of just saying yes. So as he goes up the ramp, he gains some potential energy. And the potential energy he's going to have once he's up the ramp, the GPE final, is going to be equal to 50 times 9.81 times 50, or basically just half of what we got earlier. So 49050 by 2, it's just going to be 525 joules, which means he'll be left with the kinetic energy at the end of this minus this. So I'm too lazy to write it out, so I'm just going to calculate it and write the final answer over here. 072.5 joules. That's what his final kinetic energy is going to be once he reaches up here. So which means not only will he have enough kinetic energy, but he'll probably be fast enough to do a few flips also. Now you can use they may ask you to do things such as find his final velocity, or maybe they may link it to a projectile motion question from here, but you know enough to get through those. And that should be it. Does that look good to you, or do you want me to go over something else? Oh, the guy disappeared. Oof. Can you do my midterm at the end? I may have enough time to do that. Okay. But anyways, any questions before I move on to the next part? All right, I'm just going to assume that we're all good, and I'm just going to continue to the final part, momentum and impulse. Well, now it's time to get rid of this mess of a working and drawings over here. Come down here. Yeah, thank you. Okay, so the last part, momentum and impulse. Linear momentum, given by the sign P, is just the product of the mass of an object and its velocity. P equals to mv. Now, using momentum, we can define Newton's second law in different words. We can say the net force of an object is the rate of change of momentum of the object. Now, how do we end up with this definition? Well, let's take a look into it. So earlier we said our force is equal to our mass times acceleration. Now, we know our acceleration is the change in velocity over change in time. So force is equal to mass times change in velocity over change in time. Now, if we have an object with constant mass and there's a force acting on it, well, our mass is going to be constant, and the change in momentum is just going to be equal to mass times the change in velocity. So therefore, we get force is equal to change in momentum over change in time. And that's basically Newton's second law in different words. Now, impulse. What is impulse? Well, impulse is simply the change in momentum. Not the rate of change of momentum, just the change in momentum. It's equal to delta P, or as we can rearrange this formula over here, we can get delta P is equal to force times change in time. And this is equal to your impulse I. Yep. Now, law of conservation of momentum. Well, this is simple. It's just that when you have no net force acting on an object, there'll be no change in momentum, thus momentum will be conserved. Yeah, that's all there is to it. So basically, if you ever have to do a momentum related question and they ask you to calculate the final velocity of an object or the mass of an object, all you need to do is sum all the initial momentums and make that equal to the sum of all the final momentums. And then you just pretty much figure out what's what. And the final part, elastic collisions. Elastic collision is simply this states that uh, the sum of the total kinetic energy before and after the collision is the same. Yeah, that's really all there is to it. It's pretty much just saying that a kind of collision where you don't really have any loss in energy. That's an elastic collision. There isn't much there in momentum, and they don't really ask much about it, so that's really all there is to it. You're not allowed to go from I do whatever I want, man. Like as they say in the home country, meri marzi. Okay, cool. Do you have any questions or anything you'd like me to go over? All right. I am going to assume that's all for today. I'm gonna hang around for a bit, but in case you guys have any questions. But this is pretty much the end of the session. Thanks for attending. Hope you have a great